Good afternoon and welcome to another Webinar Wednesday. Today we are joined by James Freeman, Multi-Vendor Modality Manager, PET, CT, Nuclear at Philips Healthcare. Webinar Wednesday would like to thank our sponsor, AllParts Medical. AllParts Medical provides multi-modality, multi-OEM replacement parts from its 158,000 square foot facilities in Nashville, Tennessee. In addition to parts sales, AllParts also provides customers with an extensive array of in-depth training classes and technical support before and after the sale. An ISO certified quality management system helps deliver an industry-leading warranty rate. So for more information, please visit allpartsmedical.com. Now, just a quick reminder to save the date for our fall MD Expo, which will be held at the Renaissance Dallas Addison Hotel in Dallas, Texas, from November the 10th to the 12th. So please join us for 3 days of education, networking, and the latest advances in medical technology products and services. For more information and registration details, please visit mdexposhow.com. And also a reminder to please join us for our HTM mixers. Our first mixer is being held at the Omni Interlochen Hotel in Denver, Colorado, and that's May the 15th and 16th. And our second mixer is being held at the Hyatt Regency in Milwaukee, Wisconsin, and that's July the 31st and August the 1st. Mixers are a slightly modified, smaller, shorter duration and less crowded event that still provides valuable continuing education, networking and vendor engagement opportunities. So for more information and registration details, please visit htmmixer.com. We also have a milestone to celebrate here at TechNation. We turned 15 this year, and who better to celebrate with than our readers? So TechNation invites readers old and new to help celebrate its anniversary with 15 prizes and a monthly time capsule in the magazine. So for more information and your chance to win, please visit onetechnation.com/contest. Okay, today's webinar is eligible for 1 CE credit from the ACI, and you can obtain your CE certificate by completing the post-webinar survey, which will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 CE credit, and you'll be able to download the certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us at webinar@mdpublishing.com. Okay, let's kick off today's webinar by giving away one of our Swiss Force Meister multi-tools. So using the questions feature on your dashboard, let me know the answer to the following trivia question. April is International Guitar Month. Which musician is regarded as the greatest and most influential guitarist in rock history? I'll reveal the answer and our winner at the end of the webinar. We'll be wrapping up today's presentation with a live Q&A, so please submit your questions anytime using the questions feature on your webinar dashboard. Now, as I mentioned earlier, our presenter today is James Freeman. So James, you may begin whenever you're ready.
All right, well, thank you very much. Again, I'm James Freeman, multi-vendor CT, PET CT, and nuclear modality manager. And so we'll get right into it. So I have a personal background in CT for a long period of time, and we'll discuss that. We'll go through the functions described on the screen that you can see, advantages, system overview, how images are made, common issues with CT, kind of cost to serve elements on how we view them, and how CT is enabled, for AllParts to deliver secondary tubes to the market, and CT it supported AllParts as well. So in the 1970s, I was in the Air Force. I worked radar and F-4 Phantoms. So a few of our audience probably weren't around by then, but I added a picture to the slide deck here to show you what F-4 would look like. So I was stationed in the Air Force and overseas, both in the US and overseas, and worked radar. So my electronics started realistically in 1976. Then in the early 80s, I started with an ISO OEM organization, and installed some of the first CTs at hospitals in 82, 83 time period. So obviously I've been around a few years. I've been with Philips for almost 21 years. So we're been around a little bit. I've actually been scanned by the CT scanners that I've serviced, and so have my family members. So understanding how CT impacts our lives, I directly can attest to that as well. So CTs are used at hospitals and clinics, as we know, but emergency urgent care, neurology, angiography, abdominal and pelvic, and oncology. With regards to the emergency urgent care, CT is one of the only modalities within the imaging train that actually is part of the trauma center rating for a hospital. Availability of a CT scanner allows obviously patient care to expedite pretty quickly. I know x-rays are used at times as well, but CT can do a number of things very quickly with image recon, that we can look at soft tissue, bone, a lot of different things in different contexts using different algorithms. Also, CT was the first device that came into being allowing direct view of image to brain tissue and looking at the whole brain and not just artifacts within the blood vessels or whatever. So it was the first device. We look at images kind of as a slice through the patient versus flat or 2D images. And we also use a metric that we call CT numbers. So we can determine the attenuation coefficients for different materials within the body and assign those grayscales and adjust those grayscales as well when we'll look at images. So some of the advantages, obviously, over 2D is we could look at different areas of interest. We can magnify, we can change the algorithm to enhance bone versus soft tissue, and both the other way. And so one of the challenges with CT is obviously we use X-ray quite a bit. So there are, like, an X-ray, chest X-ray may be last only 1 or 2 milliseconds, 3 milliseconds, where when we scan a whole body from the pelvis all the way up to the upper chest, we may be dealing with, a few minutes worth of scan with X-ray on at low techniques. So dose is higher, as we know, so we have to manage dose. And there's algorithms to help minimize the dose that we expose the patient to as well. So one of the things that we always try to do is make sure that we are doing the best that we can. So with regards to neurology, this is an example of what CT first came to the market for, was head scanning. EMI was the first scanner in the market out of England, and EMI then proved the technology, and all the other OEMs followed suit with their own versions of a CT device. EMI worked with Dr. Hounsfield to actually deliver the first CT scanner to the market. And so CT stands for computerized tomography. So that C really is important. As the speed of computers has increased, so has our ability to reconstruct images, use more advanced algorithms, and produce images quicker. When I first started with CT in the early 80s, it would take a minute and a half to generate one image. Now we can do 45 or higher with these graphics processors now integrated in the computers. So examples here, we see the brain tissue is in the gray matter. And then on the top ones, we see just a plain scan. And then the bottom two, you see it highlighted in inserts there, which basically is iodine within the veins. So the upper one was without contrast, the bottom one's with contrast. So we can even use contrast to help intensify vessels so we can view them directly. So also with regards to the chest, when we scan the chest, obviously we can see the heart and the lungs. So the lungs are dark in the top view because we have windowed and leveled which CT numbers we want to identify, which part of the grayscale. So we can then better show the heart, or we can adjust to better show the lungs. The two images below are reconstructed images in a context to basically show how the lungs and all the tubules interact with the body. So you could see items as well in that. So the image on the left is an artificial colored image. we can take the CT numbers that we see, okay, the attenuation coefficients, and assign them on a false color as well. We can take the whole volumetric data set and rotate around it once it's been created. So when we scan a person or a head, we scan that torso into a cylinder of raw data. Within that cylinder of raw data, as we build up slice by slice, then we can look at that from different angles. Most of the time when you're looking at CT images, you're looking at what we see on the right, which is basically an axial cut through the image. But we can view the data in other data sets as well. Also, with regards to CT, if we rotate the gantry very quickly and we gate on a certain function within the heart, we can essentially have gated data sets that it may take a few rotations to build a complete data set enough to do recon, which would be at least a minimum 180 degrees worth of data set. But at different phases of the heart, we can grab 220 to 30, 40 degrees, then overlap the next one with the next one at a given location, and then have enough built up for 180 degrees worth of data set to back project an image. And then obviously CT is very sensitive to attenuation coefficients. So we can see very detailed soft tissue. Bone, which is calcium, is in the upper end of our normal CT number range. So that would be what we would call plus 900. If more soft tissue is more water-based, right? So brain tissue may be 38 plus or minus 15 CT numbers. Liver will have a given CT number for normal standardized liver. And so we can actually use regions of interest and measure what we're seeing on the screen. We don't have the ROIs here, but as you can see, we have very good detail of what anatomy we can see in the body. And then lumbar spines. With CT, bone causes artifacts. On the older systems, before there was algorithms to compensate for that, there would be a lot more bone scattering and ghosting. On the newer machines, it's much better. MR is used also to help with soft tissue and bone interference with regards to each other. So you'll see a lot of knee joints and elbows and shoulders done more on an MRI because of the high calcium bone content. But in this case, lumbar spine, looking at the interdisc spaces, those kind of things as well with CT. So definitely a whole body scanner. So let's see, go back to this one. So we get into the CT scanner as we see it right here in this design. This is what's known as a third generation scanner. There were first generation, second generation, third, fourth, and even fifth. The difference is it's not, the generation is more of a topology of how we acquire the data. So a third generation in this context allows us to have multi-row detectors, and we spin all of this around the patient to build up at least a minimum of 180 degrees worth of data that we will then back project. 360 would be better, but a minimum of 180 degrees is required to produce an image. So as you can see, we have that green projected to the detector. That detector then converts that X-ray energy into visible light through a process using a crystal. That crystal then has a photodiode behind it, which then turns it into analog data that then we digitalize. So we have quite a number of channels, and then we add rows to this as well. And so with the rows, then we collect all this data through the data acquisition subsystem and transmit it to our recon computer that will then assemble all that data on the hard drives as a cylinder of raw data. And then we'll process out of that raw data a completed image that you get to see on the screen that would be called a slice, okay? So the example on the left is a single row with a little bit of spacing here. As we do a helical scan around the patient, we're building up that volumetric data set. So we'll have a minimum of at least 180 degrees where needed. Now, with that, we would have the collimator narrowed down, and as we scan, we're producing a certain amount of dose for that one slice. Now, as we add 3 more rows, in this case a 4-row detector, as we spiral around the patient. We're building that volumetric data set quicker, but realize from an X-ray energy perspective, we have to have 4 times the energy to be able to have that same amount of dose per slice to create that image that we would like, the quality of the image. So that's one of the reasons why we have an increase in X-ray tube capacity as far as energy that we have to deal with as well. And then, as you can imagine, we go to 16 and 64 slices and even more. There is a lot more energy that we have to produce more instantaneously for the X-ray tube. So this is an example. The first slide in the upper left corner is basically what we would be scanning in this context. And we have 2 views that we're basically collected from this. So to the left, this would be a grayscale view of the smaller circular object and the larger one interposed over each other and attenuated. And then another image would be projected downward. And as you can see, we would have a grayscale representing the smaller circle with a really light availability on there, and then the larger one attenuated even more. Now, the next view, which is where it shows number 2 up there, would be in a computer matrix, taking the raw data that we received off this scan and then back projecting two from 2 different angles, 90 degrees opposed to each other. And that would build up this representing that image in completed recon data. As we add more and more views or samples, depending on the OEM, we will then build up more and more of the image, where you have 8 and then 16 and then 32. But something actually starts to show up when we do this, and that is that ghosting that you see, that artificial data that wasn't an original has built up because of the processes and the noise that we have during the acquisition process and the recon process itself. So we have to add something called a filter. So we take the data set and we run fast Fourier transforms through the data, and basically we're enhancing and de-enhancing certain frequencies. So this is an example of what we would be doing. So on the left, we have an example of maybe a rod that we scanned. We run it through an algorithm. Now we can take that algorithm and have smooth it. So smooth would be low changes or small changes in CT number in the sample. Sharp would be higher changes like bone, or somewhere they would call it detailed in certain manufacturers. So we can pick those algorithms. So one thing that can apply here is the raw data that we have on the left, we could process it through one of these algorithms and get an image, a whole image set. Then we could reprocess this data set again using another algorithm and have 2 sets of image data processed from 1 set of raw data, which is exactly what we do when we deal with certain scans like head scans and a number of other things to enhance soft tissue versus bone. So we can use different algorithms. High frequency algorithms would be more bone-based. Soft tissue ones would be more of the lower frequency response, small changes. So this is an example of the graph would be that peak that you see at the bottom left, then transformed with a frequency response filter into what we would see with that plot. So we get some negative edges. So those negative edges are actually what we would call a recon artifact. They're part of the data set that is part of CT. So here we are back projecting the data as before, but now with an algorithm applied. As you can see, it sharpens up the data, and then down at the bottom, the center one that says 128 has a filter applied, and then the one that 128, no filtering, obviously, without an algorithm. So all CT scans have applied filter to them. So if you just went up to a CT scanner and start an acquisition, they would use what they would normally, most manufacturers call a standard algorithm, which would be a mid-range filter. It doesn't enhance soft tissue or bone. It's somewhere in the middle to give an image. But as the technologists do the scans, they will pick the appropriate protocols based on what the doctor had ordered for that scan series. So we call this filtered back projection. So one of the things that we could do in CT that we do quite a bit working with a physicist is image QA. And in that image QA, Dr. Hounsfield created a scaling system. So it's known as Hounsfield/CT numbers, synonymous with each other. So some documentation you'll see HU, and other ones you'll see CT #. They're equivalent, the same. This shows you how we derive it. So what we do is we scan water, we scan other materials before we scan a patient, and we create basically a calibration file. Each detector element, the crystal, the A to D circuit that converts it, and the amount of coefficient coming out, not off a straight shot through the image, but maybe through the angle of the X-ray beam as it travels, will be compensated for those calibration files. So at the end of the day, water will be 0 on the scaling system, but this is not tap water at your house. This is distilled deionized water as a standard. So one of the things that we can do a quick check with is take a gallon of distilled deionized water, put it on the scanner, and scan it to see if water is 0 plus or minus spec. In most cases, that's 4 CT numbers plus or minus. Air is a -1000, so when we scan air, air changes daily, so we have to calibrate our machines. So air cals are basically updated almost on a daily basis as we basically get the scanner ready to scan patients. So we do tube warm-ups, we do air cals on a daily basis. And bone approximates a positive 1000, so it's in the high 900s. So using these scaling factors, we could create basically a graph of what other materials would be when we scan them. So this is an example of what we're talking about here. So we see water in the center of the scaling system on this graph on the far left of the grayscale. And then we see other materials as well. And then we can narrow down into the grayscale. We can expand this grayscale or narrow it down based on these CT numbers. So that's exactly what they're standardized CT numbers that we typically see on grayscale. So if you notice, gray matter in the brain is over here between 40 and 50 on the CT number. So if there was a cancer or something that's abnormal, that would be identified by being a CT number out of that range. So as we narrow down our grayscale and make white or black on here within those ranges, we can better view that image data. So the data is there, but based on the way we window and level it, we can enhance lungs versus brain. And so the techs, when they take pictures, sometimes will result with defaults for some of these in the protocol as well. So they'll film them in multiple views with multiple windows and level settings to enhance the material or image that we're looking for. So the image is not just a flat image, it has depth to it. So when we do a 5mm slice or 10mm slice, we're averaging all the detail in that cut. So as we get thinner cuts on a CT scanner, it better represents, as we page through these images, more of what the anatomy is on the Z-axis. So we're looking at X and Y here, and Z has depth. So one of the things that we look at on the screen when we're looking at a CT scanner is how the data was collected, which algorithm was used, also the slice thickness, the KVMA, all that is displayed. In this case, it's showing a 512 by 512 matrix. Some of the newer scanners do 1024 by 1024. Some of the old scanners that from the early 80s did 320 by 320. So this matrix is really kind of designed with the intent that a doctor would look at the images. So the higher res images, obviously the human eye can only see so much. Grayscale is limited as well to 256 steps for the same reason. So every element on the screen would actually be considered a voxel. You just have to know what the slice acquisition was, whether it was a 5mm or 1mm, to know as you page through that a completed data cylinder, where you would be located within that patient. So this is the same image, completed image. We just are changing the window level settings to enhance what we want to see. So on the left side, you can see we've got the window level settings and the width of the window width, set to air being somewhat closer with the -1000. So we're looking more at the bronchial tubes, the lung tissue, and what's going on there. If you would see any calcification, obviously it would be extremely white there because it'd be a number way out of that range. So anything above a certain range would always be whited out. On the other hand, same image data, we just changed our view of it using the window level setting. So this data set, the patient data set, can be modified like this for doctor viewing at any time, as long as they have the DICOM images. So there's pictures, obviously, they're printed on film that are would be maybe one or both of these, but at the longest at the workstation, the doctor uses a DICOM workstation, can look at this data set and move the window level to enhance what he's trying to view as well. So some of the things that we use in the United States is called ACR Phantom. And instead of actually using distilled ionized water as a source, there's a plastic material that represents what the attenuation coefficient of water would be. So in this phantom, we use to validate it. This is an OEM independent phantom. It is the American College of Radiology's phantom that we use in the United States. Overseas in Europe, they use the Kaplan phantom. For the same purpose. It has some of the same elements into it, but as you can see, there's another things we check with regards to CT. So polyethylene has a -97 Hounsfield unit or CT number, water 0, or simulated water as it's called. Acrylic would be a +120. If you take those ranges right there, you're dealing with most of the soft tissue in the human body. So this phantom is representing what we would see on that. On the extremes, we have the bone that's a +910. There's a spec for this phantom as well. It's like plus or minus a few CT numbers as well that we would expect as well with our certification of the phantom. And then there's usually a hole in the phantom that represents air. Okay, and then the lines that you see, the sitter would be representative of different line pairs as far as 1 millimeter, 2 millimeter, 5, 10. Okay, so that we represent, that we see that full depth of that. Also, to verify our measurements, when we're measuring items within the patient, we have to validate that our scaling, our reconstruction actually matches what's in the patient. So you'll see 2 pins in the phantom in the upper right. That represents a distance that we should be able to measure on our CT scanner and get 100 millimeters between those two. That tells us when our screen reconstruction is good. Then we have pins, as you can see down at the bottom, that represent different items, and that's in a soft tissue window range. So that could tell us whether our low contrast detectability is good. That's a small change in CT numbers. Okay, there's only like 6% difference between these, though you can see it on the screen here. It's much harder to see actually when the phantom's reconstructed. And then obviously we have different line pairs represented by the numbers you see there. So example of a rough block diagram of a CT scanner, third generation CT scanner is the X-ray tube with the X-ray controller. Okay, the gantry rotating, we have to run that speed. We control the speed, we generate a view. Somewhat as a reference point, we'll have an encoder as we rotate around, and that'll trigger a sample from the data collection subsystem, okay, DAS. And from that, we will take those views and transmit them to an image reconstruction subsystem that will then copy that raw data to a disk set that later on it will pull back in queue to reconstruct and then send a completed image to the computer. So operator's console is running the main computer that reaches out to all these other controllers to drive it. So we'll be spinning the gantry and then also driving the table through at a given rate. So we're building a volumetric cylinder up. And then the mass storage that represents on the computer at the end of the computer is actually a DICOM image that's stored there that will later on be copied, transmitted by DICOM to a DICOM server. Okay. Then we get into the real details. This represents a GEVCT 64 slice. As you can tell, even the controllers and the subsystems in there, there's a lot of things going on at a given time. So we have a lot of hardware moving at the same point in time as we're generating high voltage for X-ray generating the X-ray beam, controlling the collimator, triggering the detector to receive that data, transmitting that data to the recon subsystem, and then ultimately reconning that data, and then having a completed image displayed to screen. So a very quick process. A lot of things to relay here as far as how we troubleshoot a machine and make sure everything's working. So this represents more of that detail in a more simplified view, so that we can show the name of these are particular to the VCT, like Jedi generator control. We'll deal with the high voltage inverter, the tube, the tank, and producing X-ray. And then we'll have the collimator control, and then we have the DAS control. So those are all on a rotate ring that we actually have what we call slip rings that transmits the data either through bushes. On the newer systems, we use RF with fiber optics feeding and receiving from the RF transmitter rings, and then we'll have hard rings for power as well. So as you can see, the walkthrough is somewhat the same, but as you can see, then we have DAS interface processor in the lower left. That's receiving the data, the raw data, and that's been saved into the hard drives there. And then that process, then the host computer is integrated. So we took recon and the host operating system, and because of the power of hardware now, all integrated into, in most cases, one computer now. This would be an example of an older console where we have the host operating system. In case of GE, that's a Linux machine. That's what the operators are interfacing with. So we have a monitor for scanning, a monitor for image recon display. And so the host is then working with the DIG, which is basically the controller for recon. And the verb is a special added recon for high-speed recon. And then the high-speed data array, which is the raw data array that is used for the recon subsystem. So the recon subsystem is much bigger than the host in this one. So one of the things that we deal with is X-ray tubes. So X-ray tubes are not very efficient. So if we put 100 kW in, get 2 kW of X-ray out, and 98 kW of heat. So as we talked about earlier, when we did a single slice scanner to a 4-slice scanner, in the case of we had a 20 MA or, for 1 second, all right, then now we would need 100 MA, or yes, would be 80 MA for a 4-slice to have the same dose. So obviously instantaneously in that same amount of time, we have to have a bigger anode target to dissipate the heat. The focal spot and the angle of the target would stay the same, but the tube diameter would get bigger because we're trying to spread that heat load out over the target and then move that heat load off either through air cooling, and then most of these systems are oil cooled. So we're spinning that tube at about anywhere from 8,500 RPM to 10,000 RPM. So we're spinning that anode that much. And this whole assembly is being spun around the patient as well. So we're showing a single filament here, but we'd have more filaments as well. So most CTs up to 64 slice, 128 use a 7-degree target. And then we get into the 256ers and higher, and that uses a different 11-degree target. So I'll go back just a second. So one of the things that we do on the tubes basically are our printer cartridge for CT. We use a lot of energy, and with regards to that energy, there is so much energy placed here. We have to make sure that during PMs, fans are working, all the heat exchanger filters are all clean. So we're moving a lot of heat. The entry room gets really warm. There are a lot of fans in there to manage temperature, okay? One of the highest expenses on a CT scanner is the X-ray tube here. And on some machines, we've seen this tube cost $250,000. So we need to be good at qualifying that we have a bad X-ray tube. So this is showing an X-ray generator from the VCT. So we have the inverter being driven with a high voltage tank, and that is a tuned circuit. And in that tuning the circuit, we could control the frequency that drives the high voltage tank, and that will control the kilovolts or a kV. So we're dealing with up to 140,000 volts. And then we also have pump circuits and rotor circuits to spin the anode target. Okay, and filament is actually what we use to control the MA. So as you can tell, we have a lot of processes just wrapped around the X-ray tube as well. So the detector side of it, the detector itself is not seen here. There's that plate covering it, but the elements are right behind that plate, feeding each of these converter boards. And so we are doing with 57 detector modules in this case. These detector modules are FET-based, which means that they are highly sensitive to static electricity. So whenever a service engineer is in this area, not only are they dealing with normal static issues that they would expect in a computer or anywhere else, but the sensitivity is so much higher that they definitely have to be grounded when they're in this side of this subassembly. So we have calibration vectors for every one of these. This detector has 64 rows in it with this number of challenges. So with regards to that, we have a lot of cal data. So when one of these modules is changed, we actually have to recalibrate the machine. So X-ray tubes are a common issue that we have. Sorry. X-ray tubes are the highest expense that we have. Then the next highest expense would be X-ray generator parts that support it, high voltage tanks, and then eventually computers, and then detector modules. We see detector modules that crystal will age out. Crystals and X-rays do not like each other that often, and so we'll see a degradation of the crystals within that module. And that will it's radiation hardening that will decrease the transfer function of the detector module. And then the converter boards convert that light energy from the photodiode into an A to D circuit, which will then give us the digital data going to our raw data. And then we have obviously the gantry that we have to deal with, axial drive, motor amplifiers, and then patient table. The table is always going up, but only in and out during the scan. We don't change elevation during a scan. So service people that we have to deal with, IDNs and other third-party providers, we're always looking for solutions. When we look at a cost to serve analysis of a machine, we're dealing with the X-ray tubes being expected about 70% of the cost of dealing with that product. Other parts like high voltage generator parts and computers about 20%. Then obviously we're dealing with service, which is labor, about 10%. And then so these can be directly impacted through better training, reducing our parts, our time to repair, and customer downtime. So X-ray tubes in particular, we have a number of them. We deal with AllParts, creating solutions, third-party solutions for the X-ray tubes because of the expense, and also the compliancy of these tubes that have all been checked to match OEM's expectations with regards to the technical documentation. So some of the newer systems like the Revolution EVO, the Maxima, those products all use a liquid bearing version of a tube. So we even see that within the G spectrum. Okay. So AllParts drives to make sure they have these tubes in stock and provided. The cost benefit is great. So also we have bays to support equipment here at the AllParts facility. So we have GE and Siemens and solutions for training for these products as well. With regards to it, we have many years of experience supporting this. So we even during repair processes, these bays are used for repair. We also use them for training events as well. So we have common feedback with the repair techs on things that they see on return parts that we may use to improve our training and our support as well of the people that we deal with. And all parts are tested on a machine. We have other third parties that may test a high voltage tank, but they don't actually spin it. This is all loaded on the scanner and validated to operate on a scanner and not just on a bench test. So that is a big differentiator of what AllParts brings to the market. So with AllParts, you can find and search for parts. You can also look at the availability of what we have for training as well. So heat exchangers, tanks, tubes, we have quite a few systems. We also have training courses here. These are some of the cohorts that we have. We have more if you look up on the website. So down at the bottom is a link for that as well. We will be adding Go training in the future, in the fall. So if I go back to the slide before, you'll see the systems here. So the Siemens side, these are almost all separated classes. The GEs or classes are more integrated because of common platforms. So the Go Up system that we have as a bay is new, and that will be at a added advantage going on in the fall. So this is a number of things that are supported here at AllParts. I only deal with the CT side. We also have X-ray, portable X-ray, and C-arms, and MRI as well, and ultrasound. So there we are.
Perfect. Thanks, James. We've got a couple of questions that come in. First one is, what is the average lifespan for a CT X-ray tube?
That's like asking the difference between your grandmom's car versus same car used as a taxi. We normally see an average lifespan of about 22 to 26 months on a normally used scanner. Okay, realize there's specialty scanners that say you have a hospital that does pediatrics. They're not going to use as much technique on their X-ray tubes as maybe somewhere where they do a lot of spines or a lot of cath lab or cardiac work. So your mileage varies. And even when we have systems that we take over on service contracts, when on the Philips side, those systems, we kind of use the general rule against the population, but individually, we've had sites that actually use 2 tubes a year, and then others that don't use but 1 tube every 3 or 4 years. Okay, but the average is 22 to 26 months.
That's great. Okay, another question here is, as metal can't be inside an MRI room, what objects or elements can't be in the CT room or on the patient?
There's nothing actually with restrictions towards that, but I'm sorry, my slide deck here is trying to get to it, but anyway, we really usually there's IV pumps, there's other hardware around that we don't have a problem with that on CT. Okay, as long as it's not introduced within the gantry, we're okay. So MR, yes, they have magnetic field. We also have lead shielding around these rooms, so there's no radiation that's leaking out of the room. The only people that should be in the room during a scan is obviously the patient.
Okay, I've got a question about training here. Where do I go to inquire about the training?
It's on the website. If you go to allpartsmedical.com, and then there will be a tab for training.
Perfect. Now, before we wrap up, James, have you got any top tips or anything you'd like to just summarize on?
Okay. Well, one of the things that we see quite a bit is that, like we said, X-ray tubes are the kind of the engine of a CT scanner. So it's not something that's easily changed out. Someone should really be trained on these products. Also, with regards to anybody that's servicing a CT scanner, has to really be safety trained to get inside the gantry to manage the energy of the high voltage, also the energy of the X-ray tubes, and also the gantry rotating, which then wouldn't be good if you lost a body part. So one of the things that we really want to enhance is that if anyone's going to service this, that training is necessary. We know a lot of people think CT is the same. Each OEM's approach to CT and the theory of CT is totally different. So we have what's applied CT theory, and then how each OEM approaches delivering that theory as a final product. There's high voltage, there's X-ray tubes, all those things are common to the theory, but how we actually do service, the software available for doing different diagnostics, and even the user interface for different scanners is different for the technologist to use as well. Okay, but it's a broad industry. It's one that I've been glad to be part of for a large number of years, but it's always interesting to see the people that we meet and people that we can help. One of the things that I did want to mention that we didn't talk about, we've had somebody give us feedback a few years ago that during this webinar, they heard that we had metal artifact reduction. And metal artifact reduction on the newer CTs allows us that if someone's got a brace or something on that's holding them steady, they can be scanned on the newer CT scanners because that artifact reduction will remove the metal. We still might have a little bit of blurriness within the image, but it still can be used to scan a patient. And so that's one of the benefits of the newer algorithms that we have as well.
Great. Well, thank you so much, James, for a great and informative presentation. I'd like to encourage everyone to visit AllParts website to learn more about the services and products they provide for the industry. So please visit allpartsmedical.com. Now, as promised, the answer to today's trivia question is Jimi Hendrix. So congratulations to our winner, Dalvin Williams in Texas. Quick reminder, you can obtain your CE certificate by completing the post-webinar survey, which will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 CE credit from the ACI, and you'll be able to download the certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us at webinar@mdpublishing.com. Now, if you've missed any of our past webinars, including any by AllParts Medical, please visit webinarwednesday.live to view our whole webinar archive. We'll be back next week with another webinar, so visit webinarwednesday.live for more details and, of course, complimentary registration. Thank you once again for your time today, and I hope you all enjoy the rest of your day.